Recording?
It is now.
Great. Yes. So hello, this is our work on second order behavior in augmented neural ODEs. I'd like to start just by saying a huge thank you to my collaborators, Chris, Ben, Nicola, and Pietro. Without them, this wouldn't have been possible. So yeah, huge thank you. Okay, so just a quick outline for what I'll be talking about today. So I'll start with neural ODEs. What are they? Why are they interesting? You know, they've got some great properties and we want to know why they're useful. But also, what are their drawbacks? And we'll see that this leads to augmentation. And then I'll talk about our paper, which is on second order neural ODEs. We'll talk about the motivation for them. We'll compare them with augmented neural ODEs. And we'll look at the properties of augmented neural ODEs and how they learn second order. And we see that there are quite interesting properties there. We see how they perform on real world data. And then I'll just talk about what potential future work could be done. So a quick primer on neural ODEs. So we start with a residual network. And these have been key for making deep neural networks even deeper. So the way they work is they look at some vector x, and at layer n+1, we take x at the previous layer and add some function of that called the residual. And this is a diagram from the original paper. So x goes in, something happens to it. It also goes around here, and they're added element-wise, and then put through a ReLU. But a key observation of this is that this equation here looks a lot like an Euler discretization. So if we consider for a moment some trajectory, some x that's defined at all time, well, we can solve it when we have x of t plus delta t. It's x of t plus delta t times f, where f would be the velocity. And if you make delta t 1, then these equations are the same. And the question is, what happens when you make delta t smaller and smaller? Well, in that limit, you get a neural ODE. Can we see this diagram here? Where's my thing blocking it?
No, it's good.
Okay, great. So a neural ODE is an ordinary differential equation whose velocity is parameterized by a neural network. So that's this equation here. So dx dt is some function of xt and some learnable parameters. And so this diagram from the ODE paper compares ResNets to neural ODEs. So we see that in a ResNet, there are very distinct layers, and the data gets transformed between those. But there are essentially straight lines between the two. And then we look at layer 5 to put something through, say, a classifier. But in the neural ODE framework, this transforms very smoothly. And there are not distinct layers. And so we look at t equals 5, and that's where we look to put things in the classifier. And so the depth here is sort of the integration time. So these can be solved with just standard black box ODE solvers. And what's nice about this is that a black box ODE solver isn't exactly a black box. It's made of algebraic operations, and these are all differentiable. So actually, you can backpropagate through these ODE solvers. And so the software is all there to basically build these ODE networks. Some work definitely had to be done to make them work together, but that was luckily done by the people who made the original paper. So that was great. So what are the actual benefits of these things? Well, we start with adjoint-based backpropagation, and this leads to O1 constant memory cost with respect to the network depth. So so before we had the network depth was the integration time, so T1 minus T0, which is here. And these are the And these are the equations of this backpropagation. So you have some adjoint state here. This is its velocity. This is its initial condition. And then these are the gradients. So you integrate backwards. But it's far more useful to get an intuition for that. So here's my attempt at making it intuitive. So what we have is we have a standard neural network here, which is a multi-layer perceptron with 2 hidden layers, and a neural ODE here. So your vector X goes in, it gets transformed at each layer, and your prediction comes out. And then in the neural ODE, Xi goes in, it gets transformed according to the ODE, and Y gets spat out. And then we want to do backpropagation on this. So in the standard MLP, we need to store the values at each of these layers. And we need to store, we don't technically have to store these, we could recalculate them when we're doing backpropagation. So we could forward pass and get back to this, but computationally that's not very realistic. And we can't go backwards from Y because these aren't invertible in general. However, an ODE certainly is invertible, at least in theory. So you integrate forwards to get your Y, and then when you're going backwards during the backward pass, you just integrate your ODE backwards to get these points. So you don't need to store them because it's quite easy to recalculate them. So that's the intuition behind adjoint-based backpropagation. Your T1 minus T0 can be made arbitrarily large, and the memory cost doesn't go up. So that's a huge benefit. Basically, you can make your networks deeper without a big memory cost. Other benefits include the use of black box ODE solvers, and these come with some error management. So there'll be some tolerance for how much these can diverge from the true solution. So that makes nice controlled sort of networks. Ordinary differential equations are well established theoretically. These are hundreds of years old, going all the way back to Newton. And basically what this means is we can use these theorems to help guide us build new architectures. And you know, yeah. And also another thing is these are continuous in time, so we can model a time series. So if we look at a neural ODE again, we previously used T to represent the network depth, but that didn't have to be the case. So consider where we actually look at this trajectory at these times. And we can actually look at X at T0 at this time and at all the subsequent times. So if we get a time series, T does not just have to be the network depth, but it can model, it can represent the time there. And so that's where I think actually these neural ODEs will become very good, because ordinary differential equations were built to model time series basically. And now adding a neural network on top will just make them better. So some examples of where ODEs have been used. You have these predator-prey cycles. So that's the Lotka-Volterra equations. So you have some fox here and some rabbits. And when the fox population is low, the rabbit population grows. When the rabbit population is large, the fox population grows, and so on. We have examples from chemistry. So you have, rate of reaction is a differential equation. And we have things like fluid mechanics as well. And then there are many others. So stock markets, biology, epidemiology, they're all modeled by ODEs. But what are the drawbacks of neural ODEs? Because they're not perfect. They're quite new, so there are still creases to iron out. They can be slow to solve. So you can get what's known as a stiff ODE. And what happens is you get some function has been solved and it's approximately constant. But if you zoom in a lot here, it's oscillating quite a lot. And so these local variations are very small compared to the actual function. but to actually solve this would take a long, long time. You must solve the whole trajectory. So if we get some value at t equals 1.2, and then we want to get another one at say 100, then you actually have to solve everything in between to get to that. So these things can be slow to solve. Another drawback is that they have a limited representation. So they are limited to homeomorphisms. And what does that actually mean in practice? Well, consider this task. We have a ring of points that we classify as red, and this little blob of points we classify as blue in the middle. And because this has to be a homeomorphism, the topology is preserved. So we can manipulate this how we like, as long as the blue points are always surrounded by the red points. But to classify them, we need to be able to draw a line between them. And this can't be done because the red points are always surrounding them. So I have a GIF of that, of Neural ODE trying to learn that function. And you can see the blue points trying their best to get out, but they just can't do it. And so the classifier would probably draw a line sort of here, getting some blue points and some red points. But yes, it's something that's reasonably simple, can't be done by Neural ODE. But there's a very elegant solution to this, and that's to augment the space. So we get augmented Neural ODEs, or we call them ANODES. And we augment the space with more dimensions initialized at 0. So we have our vector x, and we give it more dimensions a, and a start at 0 there. And then we evolve the ODE in that higher dimensional space. And so what does this do? Well, it's been found experimentally that this speeds up the ODE solve. So the number of steps the solver takes has been found to be lower when you augment the space. And also it means that you can solve these rather trivial functions though now. So what we do is we add one more dimension, and the blue points can just move up and the red points can move down. And now it's very easy to draw a hyperplane between them to classify these points. Okay, so that's the introduction. Now let's move on to our paper. And this is on second order behavior in augmented neural ODEs. So what do we look at? So we look at second order neural ODEs. So that's ODEs that are defined by an acceleration, not a velocity. And then we look at how these augmented neural ODEs we just seen, how they compare. So we start with some second order ODE, or we call them SONODEs. And so we start with how do we mathematically represent this? So we have an acceleration, and it's equal to some function of the position, the velocity, and time. And then we have some initial conditions. We have an initial position and velocity. In terms of actually implementing this, we use some coupled ODEs, which is fairly straightforward. So we have dx dt is v, and dv dt is f. And so that means the acceleration of x is f. And then the initial position is given to us, and the initial velocity is represented by another function of the initial position and initial time. And so why would you even want to look at second order? Well, I came from a physics background, so sort of Newton's second law instantly spoke to me, which is classical physics is can be described very well by forces and accelerations. And so you have something like projectile motion, planetary orbits, or charges in an electric field, all described by Newton's second law. So these are well motivated. And what are the properties of these second order ODEs? So we have the transformations are not restricted to homeomorphisms. So actually, we look at the blue points and the red points, and they can just pass straight through each other. So you can draw a line through those and classify them correctly, very easily. And also it's forced to learn second order, which whilst it's constraining the dynamics, it's constraining it to something that's very common in physics and in other subjects. So then we looked at anodes and learning second order in general. So we look at some cosine function, which is just a standard second order function. The second order Neural ODE obviously learns this very, very easily. It's built to learn that. And the augmented Neural ODE starts with some sort of exponential decay, which would sort of be expected from a first order model. So that's sort of exponential decay there. But then it can break out of that and actually learn this second order function. And so this shouldn't be too surprising, because if we look at the functions again, we see that they can be sort of made quite similar. So we start with the SONODE equation. dx dt is v, dv dt is f, and we've got initial conditions. And then the ANODE equations are dx dt is given by some function, capital F, and dA dt is given by some capital function g. But if we were to manipulate that slightly, we could say, well, what if it learned that? So A is definitely a function of xa and t. It's just a very simple one. So we have dx dt is a and dA dt is f, and this would give the correct acceleration in x. So it's not surprising that anodes can learn second order. The only thing is this is almost true, because we've got a of t0 is 0, and so we just add the initial velocity here. Or we could say a does not have to start at 0. A can learn this g, this initial velocity here. But there is a more general way that these anodes learn second order, and this is where we start seeing the interesting properties. So we start again with these dynamics. These are the dynamics we want to learn. The acceleration is given by a function of position, velocity, and t. And then this is the anode that's trying to learn it. So we have dx dt is some function, capital F, and dA dt is some function, capital G. So we differentiate the top line of this. So we get d squared x dt squared is df dt. And we can do that just by using the chain rule. So we get the acceleration is the partial f of x times dx dt plus partial f of a, dA dt, plus partial f of t. And we have these values, dx dt and dA dt, they're given by the original anode. So they're given by capital F and capital G. So we sub those in, f there, g there, to get this. And we also remember that we want d squared x dt squared to equal the dynamics we're trying to learn. Well, I've just substituted the velocity for f here. And if we rearrange this for g, so we've taken f, we minus this term, we minus this term, that's there, and we invert this term here, we get capital G. And so for any capital F function there, we can learn some g, which will give the correct acceleration. So what about the initial condition? Well, dx dt is given by f, and so capital F can, subbing in those initial positions, can learn the initial velocity. Just to sort of summarize that, the dimensions are entangled. So what does that actually mean? And don't take this illustration too literally. SONODE has x and v, and they're very much separated. You have dx dt is v, and then v learns a different function, an acceleration. Whereas in ANODE, they're sort of overlapping, and they're all entangled in these functions f and g, and there's arrows going all over the place. And again, don't take this too literally. But yeah, so those dimensions are entangled. And so we have f learning the initial conditions and g learning the acceleration. But so this leads to very interesting properties, or we thought they were interesting anyway. So this was the equation for g given f that would guarantee the correct acceleration. And we see that this term here needs to be inverted, but there weren't constraints other than that. So if the dimensions of A were less than the dimensions of F, well, we could have a a pseudo inverse here instead, and this would still learn the dynamics. And what does that mean in practice? Well, consider this 2D function here. So this is a 2D second order function where in each dimension there's damped harmonic motion. F has the same dimensions of the input space, by the way. And so we take this 2D function and we augment it with only one extra dimension. And we can see though that the anode has learnt the trajectory. And why is this interesting? Well, if you consider a second order neural ODE trying to do the same thing, it needs to have 4 dimensions. It needs to have x, y, and then the velocity of x and the velocity of y. And so SONODE had to do it with twice the dimensions, and it has to every time, whereas ANODE doesn't. And so it can sort of, because it entangles its dimensions, it can efficiently learn the dynamics. And then, but we see that this leads to something else. We see it leads to interpretability issues. So we have the function again, g given f, but we haven't said f takes any particular form. So let's say we learn a particular f and g, but that wasn't unique. We could learn a different f and a different g, and we'd still get the same dynamics. So if we look here at this 2D function, we have the function here, which is the black dotted line, and what ANODE learns, which is the yellow line. And we can see it learns the function absolutely fine. But then we also plot what the velocity should be, this dotted blue line, and then what the augmented dimension learns. And we tell it to start at the initial velocity. And we can see between training runs, it learns completely different things. And that's because nothing said it had to learn the same thing. So what were the chances that it would really? But we show in the paper that because SONODE's dimensions are disentangled, then they always learn the same thing. So this is 2 separate training runs. We see that the learned velocity is the same as the true velocity, and that they have to learn the same thing. And so what does this mean? Well, if we were to use this for applications in the natural sciences or physics, for example, SONODE makes it reasonably easy to recover the force equation, because that's what it learns. It learns the acceleration. Whereas ANODE is learning this sort of coupling between real space and augmented space. And that does not make it as easy to recover that. Whereas with SONODE, if you get the force equation, you can then use that in your theories and look how that works with, under different conditions. Okay. So then we look at the advantages of SONODE. So we see that on a second order system, these train faster. So we looked at 30 oscillators. Each one had the exact same ODE describing it, but they had different initial conditions. And we let the models have the position and the velocity. And so the loss was the mean squared error of the true position and velocity and the learned position and velocity. And so how did the models actually learn this? So for a vanilla neural ODE, we gave it x and v, and it could learn dx dt and dv dt. For a second order neural ODE, we forced it to say dx dt is v, and then it would just learn the acceleration. And then in the augmented neural ODE, we said dx dt, dv dt, dA dt, you can learn any functions for those. And so what we saw was, because second order neural ODEs already have that inductive bias in place, the loss just drops very quickly. All it has to learn is the acceleration. Whereas neural ODEs and augmented neural ODEs also have to learn second order as well. And also what's interesting here is when you know your system is second order, you can put all your parameters in your acceleration. You don't have to learn second order. So dx dt equals v requires absolutely no parameters. So all the parameters can be here, so that it can be more efficient with its parameter usage. We saw it was more robust to noise. So what we did was we trained these models on a sine curve from t equals 0 to t equals 10, and then we extrapolated from t equals 10 to t equals 15. And so we've got some figures here and it was given Gaussian noise centered on 0 with different standard deviations. And as we can see from this figure here, as the noise gets larger, SONODE is able to sort of keep the loss down, but ANODES grows. And actually, by the time we're at 0.7, these sine curves only have an amplitude of 1. So by the time we're at 0.7, that's very noisy data. So I'd focus more around here, which is where it's winning. And we sort of saw this earlier anyway, in the train when these curves were training. So the SONODE curve changes very slowly and fits the cosine, whereas ANODE is moving around quite a lot, and so small changes in the parameters, or at least the gradients, are larger, but those small changes can lead to big changes in the actual function. And as mentioned before, we know that SONODEs are more interpretable than ANODEs because they always have to learn the correct acceleration, functionally at least, whereas ANODEs can learn some quite weird augmented trajectories and still get the same trajectory it wants to see. Finally, we see that on systems we know for a fact are second order, we get improved performance. So we looked at something known as the silver box dataset, which is an electronic implementation of a Duffing oscillator. So the equation for that is this, which is quite easy to break down. So we have an acceleration, a damping term, a spring term, a nonlinear force. So this is what makes a Duffing oscillator different to a harmonic oscillator, and then some sort of driving term. And these are some phase space pictures of a Duffing oscillator, so X and V, and so it does some quite interesting patterns. And then this is X against T, and so you can see this is quite a weird pattern to learn. And in different situations, this can become chaotic. But we see that that SONODEs actually can learn this quite well. So when we look at the silver box data set took two voltages. So voltage 1 was essentially the driving term, and voltage 2 was what we are measuring. And so we're looking at voltage 2 here. And so we trained these models from timestamp 0 to timestamp 1000, and then extrapolated. And we can see that SONODE has learned it very, very well. And that error is quite low, whereas the ANODE error is sort of just growing. Yeah. And so just a quick summary of those advantages. When the dynamics are known to be second order, and that will apply to a lot of situations, these will be faster to train, there'll be more robust to noise, and you'll see better performance. And in general, they're just more interpretable because those dimensions have to be split up. But what are the disadvantages of SONODE compared to ANODE? Because I'm not going to claim they're perfect. You need double the dimensions, and so you can't use minimal augmentation. So as I said, for a SONODE, you need each dimension for the position and then another set of dimensions for each velocity. So you always need double. Whereas we saw in ANODE that you can represent the function. You can represent the function with less than double. And so it's not as efficient across dimensions. And also, SONODEs are constrained to second order, so they can't model any higher order dynamics very well. So we looked at this airplane data, which looked at an airplane's wing, and there was they were oscillating one side of the wing, and then they had accelerometers around on the plane, and we looked at this one A2, and this is very much not second order. This is high order. And so again, we trained from timestamp 0 to 1,000, and we saw that that the SONODE was not able to learn this as well as ANODE. So that ANODE error is lower than SONODE. And we put this down to ANODE being able to use its capacity fully, because it can do anything, because it doesn't have to learn second order. That's what I meant. Okay, so potential future work. So what would be useful is some further analysis on minimal augmentation. So we showed that it was possible, and we showed that for a 2D function, a particular 2D function, you only need one extra dimension. But I imagine for a 20-dimensional function, one extra dimension might not be enough. And so it'd be useful to see what sort of limits can be placed on that, and then and whether that's dependent on what the function is and the dimensionality. Further analysis on interpretability. So we saw that ANODES can learn quite different augmented trajectories functionally. And so it would be interesting to see, depending on the initialization, how much do those change? If you initialize it slightly differently, how much will the functional, how much will the trajectory change? The final parameters might change a lot, but how much will the actual trajectory change? Apply it to more time series. So we only applied it. So we applied it to a few time series, but it'd be interesting just to see, different second order time series as well. And then finally, the regularization accuracy trade-off. So we saw earlier that we can get stiff ODEs, and a lot of great work has been put into trying to fix that. So a lot of this has been by trying to minimize the higher order derivatives, or even or sampling different times where you want to look. And these have all been sort of for classification-like tasks where you only look at the end of the trajectory, and so you don't actually care how much it's moving. So you don't want it to move much in the middle, but you don't care what the intermediate trajectory is, because you only care about the end point. So it'd be interesting to see what sorts of regularization techniques could be used to regularize it when you're looking at a time series, because you want your trajectory to be correct as well. You don't want it to just be straight lines. But yeah, so that's potential future work that could be done. So I'd like to say a big thank you for joining us and listening. If you have any questions, I'd love to answer them now. If you think of any, that's my Twitter, that's my email, and then these are the Twitters and emails of all the people involved in this paper. Yeah, thank you.
Thank you very much, Alex. So, questions or comments? You can unmute yourself if you want to ask a question, or write it in the chat.
Why aren't people using these more widely? So, as I mentioned near the beginning, there are still some errors. So not errors, there are still some drawbacks. So we have these stiff ODEs, and they're very new. These only came out in 2018, and so they're still sort of quite. They haven't really been made useful for like large scale deployment at this stage, I would say. But there's been really great work in trying to make them more useful. So controlled differential equations by Patrick Kidger. I'll just write that. Oh, yeah. So controlled differential equations has been a great attempt at making these more practical. And yeah, and I'd just say, you know, I think it's to do with the speed of them at the minute, because if you consider an industry like say finance, they already have these models that work well, and I assume they're putting a lot of work into them to try and add this Neural ODE to it. And in my opinion, I think the best way these will be deployed is by having a Neural ODE that starts with theory. So it might be something like the Lotka-Volterra equations, and then you add a little bit at the end, and you learn that little perturbation. And yeah, great, thanks. Let's see. Are you only able to use these for extrapolation of a time series, or can you use it to classify a series? You can use them to classify a series, definitely. We didn't do that in this work, but in the controlled differential equations work, there's a really nice example in their GitHub, which is they give you these spirals, and you're just trying to classify the chirality of the spiral. So if it's spiraling anti-clockwise or clockwise, basically. And then they also do work on classifying digits. Letters. So they look at a data set where you have a time series of a pen position on a paper, and then they look at the time series and say, what letter is this? Yeah. Did you use any explicit metrics for measuring the interpretability of SONODEs? No, we didn't use explicit metrics. Essentially, we just looked and said, yeah, I can work out, you know, what that velocity is, basically. So no. But that would be a good use. That would be a good point of future work, actually quantifying how interpretable they are. Have you tried using these in generative settings? Not yet. Again, a useful piece of work, future work. I think the reason we haven't yet is because, again, these are quite new, and we'd have to be cautious in using them and then making a big claim about how well they work, and then for someone to use it in the real world on their car or what have you. So that's why, basically. But no, that'd be useful from an academic perspective, definitely. Just being cautious using it in the real world at the moment. Yeah, definitely useful to be used in sensor data, absolutely. Cool. If there are any other questions, yeah, feel free to ask. Or as I said, I'll just show my thing again. Or if not, again, these are the you can contact me on my Twitter or on my email.
Great. So any more final, one more question or comments?
Oh, great. So what applications outside engineering? Oh, there are, I mean, what applications are there for ODEs, really? So the original motivation for me was from physics, because, I mean, I will say this cautiously because I haven't done physics for about 8 months, but basically all of physics is ODEs, or not ODEs, sorry, differential equations of some sort. Maybe some thermodynamics isn't, as far as I can remember, but you know, relativity, quantum, all that is differential equations. You know, economics, so there are lots of ODEs in economics. Quite a relevant example is epidemiology, so the SIR model is an ODE. Biology, so at the minute I'm working with a student to try to make an immunity model based on ODEs. And yeah, just anything really with a time series. So a really good example, and one that I'm quite interested in, is medical data. So if you consider someone checking into hospital, they'll take your blood pressure, they'll take a blood sample, and it will take some time for that to come back from the lab. And so you want to model what's going on in between those two times. And a neural ODE, or a controlled differential equation, is really good for that, basically.
Great.
Okay.
Thank you very much, Alex, and also Ben and Nicola and Chris and Pietro. Thanks very much, everyone, for joining. And next week we have, I think, Nick Lane giving a talk. So see you all soon. Thank you, Alex, again.
Great.
Bye.
Thank you.